Hello everyone, welcome back to ECE410 Power Electronics. This is lecture 10, part number 2. In part number 2, we're going to talk about critical operating condition of converters. So what is the critical operating condition? Let's talk about this. So there are three different operating conditions for converters. One is normal operating condition is right here. At this condition, your inductor current has ripples, but inductor current magnitude is so high the ripple is small. So small ripple here. It could be 5%, 10%, or less than that. Small ripple. We call it a normal operating condition. But if your magnitude of the inductor current goes down, how can it goes down? If we have the R value going up here, inductor current will go down. But your ripple is not. You still have the same ripple. Like if you have 10% ripple, you still have a 10% ripple. But your magnitude is going down. So that means your current is coming down. So your ripple stays the same, but your current magnitude is coming down. So it can reach at a point that we follow the red line over here. If ripple goes up and down, the green line here. If you follow the green line over here, it goes up and down, but it touches. Look at it. It touches the 0 point. Right, this is the point. If you touch this one here, is the current, right? This is the zero current here, right? 0, 0. So at this point, time is 0, current is 0. So this line represents the 0 current. This line represents the 0 current. So when you touch this one, is your 0 current here, right? Right. So this point, and this point, all of them touching the 0, right? So that means your current becomes 0. Just not 0, just touching the 0. That's called critical conditions or critical value of the current right here. So, and if your magnitude of the inductor current goes lower than that, then you will experience a 0 current for a time being. This is right here, right? If you follow the red line over there. So that is called discontinuous conduction mode. Discontinuous conduction mode. So, or DCM. So this is your CCM. This is still CCM, but in a critical condition. So there's three different operating conditions, right? Normal operating condition, critical condition, and discontinuous conduction mode. So this video, we're gonna concentrate on critical operating condition. So in discontinuous conduction mode, if you go there in the next video, if you have some restriction on KVL, KCL, we're going to talk about that. We can have that at some point that both switches are on or both switches are off. We're going to get there when I get to the DCM. So again, in DCM, let's talk about DCM a little bit here. So I have to distinguish DCM and CCM, normal operating condition, with this variation over here. In DCM, this is when this part over here, when your switch 1 is on. This part here, switch 2 is on, but this part over here, both switches are off. So both switches are off, right? So that means your D1 plus D2 is not equal to 1 anymore. So that's one of the condition that you have to be careful in DCM. And for any converter, doesn't matter what you're doing, DCM or CCM, we assume that energy conservation still holds. That means the average voltage across the inductor over a period is 0, and average current across through the capacitor over a period is also 0. So, as I said, CCM, critical condition, DCM, you can go one by one. So we talked about this a lot, and now let's talk about the critical operating condition. So, in the critical operating condition, your input current here. So this is your input current, right? And this is the output here. Right? So this input current, average input current, is equal to the inductor current here as the amount of time your D1 is on, or switch 1 is on. So right here, right? And your P in, how much power coming out from the source, is also the current, this right here, is come back here, and the voltage, right? Same with the load. So average load current or output current is amount of time this switch is on here, number 2, right? This is the number 1. So it's right here, and output from the same way. So current D2IL times B out, right? So if you have a lossless converter, P in should be equal to P out. And in the critical condition, you still have D1 plus D2 is equal to 1. Why is that? In your critical condition, if I draw it over here, so this is your D1 here, and this is your D2, still D1 plus D2 is 1. All right. So if you look at, take a normal current, and what is input current, what is output current for buck boost converter. So this part over here, this input current, and this is your output current. So this is your I out, this is your I in. If you separate them, this input current, this is the output current. All right. So now in the critical condition again, IL is at the boundary. That means it's touching the zero, but not zero, it's touching the zero. That's the boundary condition, this critical condition. And still we have the D1 plus D2 equal to 1. So as I said, the same thing over here. It touches the zero, it's not zero. So IL is still positive all the time. It doesn't go zero, but is touching the zero. And same thing with if you have that inductor, if you have an inductor doing this, like if you have an inductor value in your buck boost converter, just maintaining the current like this, right? We call it critical inductance. And critical inductance value is very important. If you have find that, you can easily design any other value from there. And same with the capacitance. If your volt is doing that and just touching the zero, that is called critical capacitance. Normally, critical capacitance is not important for design because we always use a very high value of capacitance to make sure that our voltages are ripples are very small. So, and discontinuous conduction mode, if your L value is lower than L critical value, remember the L critical value where you touching the zero but not zero. If your L is lower than L critical value, you go into discontinuous conduction mode. And again, said before, switch 1 is on here and switch on 2 on here, and both switches are off here. Okay, so now let's examine the critical operating condition for the buck boost converter. So at the critical operating condition, if you see over here, this is the ICE boundary, IL at the boundary, ILB. That average value is half of the peak value. So half of the peak value. And your peak value, interesting that your peak value over here is basically ripple. Can you see that? So your peak value is the ripple. So if I use this equation we used before, you can see that your delta IL, what is the peak to peak ripple, that's actually peak value here, because you can see the your peak to peak ripple over here is basically your peak value, right? So delta IL is VL dt by L, and T is 1 by Fs, right? So now if I put this one back to this equation over here, so your boundary value or critical value of the inductor current average value is half peak. Look at it, it's half of the peak, right? This value is half of the peak. Then peak value is with delta IL, so delta IL right here, right? If you bring the equation back here, that's the equation for your average inductor current at the critical condition. And if you put T equal to 1 over F, you get this equation over here, right? And also when switch 1 is on, we're using D is for switch 1, and your VL is V in, right? So VL is V in, which switch is on. So now, also in a buck boost converter, you know that your inductor current is basically a summation of input current and output current. And input-output current relation is right here. And if I use this one, back to this equation over here, and also your I out is V out over R critical. We're looking at we're looking at the resistance, that your critical resistance at the output of the converter. You put back here, then you get this ILV over here is with this equation. If we use these two equation back to this, you get that one. All right, I'll leave it up to you. Then I also know the ILB from here, so I'm going to bring that to here. So this is my equation for this critical condition, trying to relate input and output voltage, right? And also trying to find that what will be my R critical value. All right, let's go back here. So I wrote this equation back here again, the same equation. And I also know that input-output relation over here from the buck boost converter. If I put back into this input and output relation, this one, this equation here, I will see that my R critical value is this. What this means here, if you know your L value, then you can find critical load for the converter where you can still maintain this operation, which is critical operation, right? Now if you have a R already known, then you can find also L critical value is in this equation or this equation here. What L value you have to use to make sure that it's still in the continuous conduction mode, but at the critical level. Okay. So I would say this one is more important than this one here, because load, you cannot guarantee load. Load could be different, but your L value you can choose to make sure that you have at least a what do you call it, CCM operation, but in critical condition. All right. So this equation for the buck boost converter, and same equation you can develop also for boost converter and also buck converter. And what is important here? When L is L critical, your ripple is at plus minus 100%, right? So now your L is 10 times of L critical, right? Then your ripple becomes plus minus 10%, right? If your L is 100% of L critical, then your ripple becomes plus minus 1%. So you see that over here. So if you know L critical value, you can easily find, you can design for your L value that you want at what percentage of the ripple. So again, I say that for buck converter, this is the equation for buck converter, this is the equation for boost converter. So L critical value is important. We're gonna get to that in the next lecture. Now, why is important? So now you know how to design your L critical, R critical value for buck boost, and buck converter. We're gonna stop here. The next one we're gonna go into discontinuous conduction mode.